Swayam Prabha. Digital India. Educated India.
Towards the end of the last class, there were a couple of questions after the class got over. So, I will just talk about that. I think some confusion about metric space and normed linear space and inner product space, which is a subset. And I think I made a fleeting mention, but I thought I will spend a couple of extra minutes on that. Okay. So, if you have this, let us say this is a normed, this is an inner product space. Let me draw this thing very big. This is a inner product space. Basically, what do I mean by that? I mean, it consists of vectors, okay, where, and in that space an inner product is defined. And what you know is, if an inner product is defined, automatically a norm is defined. You can define length, and if the length is defined, you can define distance. So, in this space everything is defined. Okay. In this I have norm, inner product and distance, all three are defined. But I can have, and I am just going to draw a circle here, and I am going to call this a normed linear space. In the normed linear space, only the norm is defined, only the concept of length is defined. Okay. So, I have length and metric defined, because once the norm is defined, metric is defined. The point is, this is kind of a subset of this, because only in this space inner product is also defined. Inner product includes both of this, and outside I have, let us say, a metric space where only D is defined. So, in the metric space I may not have norm, I may not have inner product. So, metric space does not have to be a normed linear space, and then I do not have a concept of length, I do not have a concept of angle, I do not have a concept of inner product. Okay. So, this does not have concept of norm or inner product. This is a normed linear space, it has concept of norm and it has a concept of metric, okay, but this does not have concept of inner product. So, a normed linear space does not have to be a inner product space, whereas the inner product space automatically defines a norm, automatically defines a metric, and therefore, if I say a space is an inner product is defined, automatically the other two are defined. So, I mean, there was some question about converse is true or not. So, an inner product space is necessarily a normed space, is necessarily a metric space. A normed linear space does not have to be an inner product space. A normed linear space is definitely a metric space, because automatically a metric is defined. And a metric space does not have to have a definition of norm. So, it is not necessary that the metric space has an inner product or norm defined. Okay. So, basically that is the kind of hierarchy kind of thing you need to have. If an inner product is defined, everything else is defined, norm and metric. If a metric alone is there, it is not guaranteed that you have a norm or inner product. If a norm is defined, metric is defined. Okay. So, I mean, just to recap, the other thing which somebody asked me is, Yesterday when we were talking about Gram-Schmidt orthonormalization, we were getting an orthogonal set of vectors, saying look, you already have an orthogonal set of vectors, which is the standard vectors which you have been using with, which you are used to working with 1 0 0 0 1 0 0 0 1, correct. And so why don't we use that orthogonal set for solving problems, okay. You could use that method, and that is what we do most of the time when we are working with numerical methods, okay. But the point is, we are not only interested in representing an arbitrary vector in terms of the basis. In addition to representing the vector that you are trying to represent has to satisfy some equation, some differential algebraic equation, some differential equation, like that pipe flow problem Ax equals b, that also has to be satisfied. It is not that I just want to represent x in terms of a basis, I have to make sure it satisfies Ax equals b, okay. And therefore, if it is only representing a vector in terms of a basis, you can use this orthogonal basis, the standard orthogonal basis, unit vectors in x, y, z direction. But I also wanted to satisfy my algebraic equation. So then you see that it becomes again solving a bunch of linear equations, okay. So we will see that. So that is the reason we are not advocating using the classical unit vectors which are orthogonal, okay. So why don't we use the classical unit vectors? What do I mean by that? 0 0 0 1 0 0 0 1 to represent an arbitrary vector, because we want to make sure this arbitrary vector also satisfies my constraint, which is my differential equation. This some constraint. What do I mean by constraint? A u equals b, because that is the vector I am trying to figure out. So it is not that it can be any u, I want to make sure it satisfies this equation. So this becomes an issue, okay. So then we lose the elegance of orthogonality. Okay, you will understand it when we do things further, okay. So I mean, that was a good question, because I mean, why waste time doing orthogonal things when you already have one orthogonal set, okay. So now let us move on. So we want to start thinking, I mean, you are used to matrices and how to use matrices and do the analysis, okay. I mean, vector multiplication and all that, but I want to basically change the way we are thinking about it, so that we can use it for other problems like in partial differential equations. So the idea is to generalize it, let us look at a function f of x, okay. So, just to make the analogy clear, let us look at y is equal to f of x. So, if you have a function f of x, then this function f is defined on a domain. What is domain? The values of x over which this f acts. Okay. So, f function has a domain, the values of x on which the function is valid. Okay. This is what you have studied in calculus. And what is the range? The values of y or f of x. Okay. So, basically what does f do? F will take domain and you get range. So, domain is basically the set of x values, okay. It could be 0 to 1 minus 0 to infinity, whatever it is, or which f is defined, and you get a bunch of y values. So, basically it maps the domain into the range, okay. It maps whatever values of x it is acting on, and you get a other set of values which is the range. Similarly, I can look at a matrix. A is a matrix which I am going to call it m by n. Okay. That means it has m rows, n columns. And the elements are A11, so the first index tells you the row, second index tells you the column. Okay. So, basically I mean this is how we denote a matrix. And what does the matrix do? It can multiply a vector and give you another vector. Okay. So, basically what does A do? V equals AU. This is just a matrix multiplication operation. Okay. Now, U will belong to what space? This is an m by n matrix. So, U has to be n by 1 and V has to be m by 1. So, what does the matrix do? It multiplies vectors in Rn, it acts on vectors in Rn. How is it acting? Just by multiplying, matrix multiplication. So, the domain is Rn and the range you get vectors which are in Rm. Okay. So, basically the way I look at it is A is mapping vectors in Rn to vectors in Rm. Okay. So, and function the way we spoke about could be non-linear, could be sin x, cos x, whatever, x square e power x. But here I am talking about a simple matrix multiplication. So, what are the way to look at the matrix? The way we are going to look at the matrix is it is a operator. It operates on vectors in Rn, n dimensional vectors, and it gives me vectors in Rm, an m dimensional vector. Okay. So, just like what the function does. So, now and the only thing we are interested in is looking at the properties of this thing in a kind of a generalized setting like we did. Now, normally you are used to discussing a matrix A in terms of things like rank of a matrix, determinant of a matrix, and then talk about the properties. Okay. But we want to move out of that kind of thought process, because I want to be able to generalize it, because if I only talk about rank of a matrix and all that, I will be restricted only to matrices. I do not know how to talk in terms of rank of a differential equation, partial differential equation tomorrow. Okay. So, because I want to get out of this business of and I want to have kind of same framework for all of them, all the different kinds of problems, I want to not talk about rank and determinant, okay, because that is restricting me to matrices. Okay. So, what do I mean by that? I am going to talk about this. So, basically A is an operator which does this, and that is what I wrote, matrices as operators. So, I am going to talk about a linear operator. Okay. Again, in a general setting, what is a linear operator? L is a linear operator if one LU is equal 0 for U equal to 0. Okay. And 2 L times C1 U1 plus C2 U2 equals C1 L U1 plus C2 L U2. Okay. What is, so if my operator acts on 0, I should get 0. If I get something non-zero, it is not a linear operator. And basically this is C1 and C2 are scalars, they belong to the field F, could be real or complex. Okay. C1, C2 are scalars belonging to F, the field, and this is like a scalar multiplication. Okay. So, C1 U1, L operating on C1 U1 is same as C1 L U1, L operating on something plus something is that plus that. So, vector addition. So, basically it can be taken inside, L can be taken inside and C1 can be taken out. Okay. So, if there is an operator which satisfies this, then you call it a linear operator. Okay. So, now the question is, is the matrix a linear operator? Answer is yes, but can there be other things? What about the derivative? D by dx, is this a linear operator? Answer is yes, because the derivative of 0 is 0. Okay. D by dx of 0 is 0. If u is 0, it has to give me 0. And derivative operator is some constant C1 multiplied by F plus C2 multiplied by G of x is equal to C1 d by dx of f of x plus C2 d by dx of g of x. I mean, this is from the property of the derivative, right. So, basically what I am trying to show is that the first order derivative is also a linear operator, and that is what I was trying to tell you, that if I start thinking in terms of operators, I am able to generalize and move away from the vector space to functions also. Okay. And the similar, you can also look at the second derivative. Second derivative will also be a linear operator. Okay. Similarly, You can check this. Okay. Now, why are we interested in second derivative? Because when you are trying to talk about problems which involve diffusion, you will have the second derivative come d square c by dx square, conduction k d square t by dx square, momentum transfer mu d square del square v. Okay. So, basically in several problems in chemical engineering second order derivative will come. Okay. So, that is the reason we are interested in second derivative. Again, so when you are solving partial differential equations later, we want to use this. So, this shift from looking at matrices purely on vectors, I want to move it away to a generalized setting. I can use it in for something acting on functions. So, this the first derivative is a linear operator, second derivative is a linear operator. Okay. All these are linear operators, and so whatever I am going to develop for matrices, by thinking of them as linear operators, I would like to see if the same things are valid for differential equations also. That is the idea. Okay. So, now can the concepts for matrices be extended to partial differential equations by thinking of them as operators. And what is the answer to the question? Yes, it is possible, otherwise we will not be doing this course, right. Okay. So, I want to linear operator is done. I want to define this concept called an adjoint operator. Okay. If what is the meaning of an adjoint operator? The adjoint of the operator L is denoted by L star. So, star tells you is an adjoint operator. Okay. And how is it defined? This is defined as inner product V with LU, V with LU must be equal to inner product of L star V with U. So, for all U and V, okay, for all U and V, but take any, I mean it has to be if L is a matrix M by N, then U has to be in Rn, V has to be in Rm, okay. Only then you can take the inner product, right. So, for example, if U belongs to Rn, V will belong to Rm. Why? Lu will be, L is my matrix A, which is M by N. Okay. So, when I do Lu, I will get an Rm vector with m dimensions, and this will be Rm. Only then I can take inner product. I can't take an m dimensional vector and an n dimensional vector and do an inner product. So, keep that in mind. Okay. They all have to belong to the same space. So, this is basically what it is. So, basically this is the definition of adjoint. If I can find an L star which will satisfy this. So, another thing is, most of you, I think in the context of matrices especially, you looked at some adjoint or ADJ or something like that, okay. What is it? Yeah, for inverse of matrices you used to do this adjoint. I want to make it very clear that adjoint is different from this adjoint. As far as this adjoint is, this course is concerned, that adjoint is useless, okay. Only this adjoint is what you have to think. So, temporarily for 2 or 3 months you can erase that definition of adjoint, because you, and this is a much easier adjoint to calculate, okay. That adjoint you have to do some cofactors and something, okay. And like he says, to calculate the inverse you are looking at adjoint. So, that is completely different ball game. So, just erase it from your mind, at least temporarily. This adjoint is different, it has got nothing to do with inverse, okay. In fact, that adjoint is what is called adjugate, and then that has been truncated to adjoint for some reason, okay. But this is the real adjoint, okay. Okay. So, now given a matrix A, how do I find the adjoint, okay. And again this, the way I am setting it up is again same fundas I am going to use, same approach I will use for differential equations. And that is the mantra you have to keep remembering. So, how to find A star for a given A, which is m by n. A is an m by n matrix, okay. So, look at this now in the context of matrices. For matrices, when I do inner product of U with V, what do we have? We write it as sigma ui vi. I mean, let us not complicate life by putting conjugates now. Let us say that we are all working with real things, okay. Once you become comfortable with this, then I can put conjugates and confuse you. Right now, no confusion, all real, so no conjugates, okay. So, U and V are belong to Rn, the way I have written it. And basically, this is the same as the dot product that you are used to taking. Take the first coordinate, multiply by the first coordinate. And another way to write this is, you can write this as U transpose V, okay. I mean you can do that, you can look at this thing, only then you can get this 1 by 1. So, this is an n by 1, this will become 1 by n multiplied by n by 1, I will get a scale, it will same as this, okay. Is this clear, or you want me to explain this? So, U is basically U1 to UN, V is V1 through Vn, and for what is U transpose? U transpose will be U1 or subscript U1 through UN, okay, and U transpose V so you do this matrix multiplication, okay, 1 by n by 1, you get sigma ui vi. Just to tell you that I can write it as U transpose V, okay. That is my inner product. Now, what I want to do is, I want to look at this is, so basically for matrices, for vectors, the inner product which I had defined earlier can be written as U transpose V, inner product of U V can be written as U transpose V, Okay. So, I have just shown that inner product of u v can be written as u transpose v. But what I want is, so now I want to take inner product of u with a v. Okay. That is what I am trying to find out, right. This is equal to u transpose a v, because this is my vector. So, first vector I am going to just take the transpose, second vector is as it is, okay. And you know that A B transpose is B transpose A transpose, something you are expected to know, okay. So, what can I do here? I can write this right hand side as A transpose u transpose v. So, basically this is B transpose A transpose. So, all I have done is done the transpose of this, and so A transpose u transpose this u transpose A from this, okay. When I do the transpose, I will get u transpose A v the same as this, okay. Now, what is this going to be? This can be written as inner product of A transpose u with v, because A transpose u is some vector. If I take the inner product of this, I will take the transpose of the first and then multiply with the second. That is what I have done, okay. So, let me just repeat what I have written here. This is the definition. I am just treat A v as some vector, you get this, then use this identity and write it as A transpose u v, and this is now my first vector, that is my second vector. So, this is the inner product of first vector times the second. You can go backwards. If you have difficulty coming like this, go backwards, it will become clear, okay. So, what do you see? So, this is going to be true for all u and v, for any u and v. So, I conclude that the adjoint for a real matrix operating on u and v which are real is going to be given by the transpose. So, by definition, what was the definition of adjoint A star? Inner product of u v, u with A v must be equal to inner product of A star u with v. So, I compare, I get A star is equal to A transpose. Basically, the adjoint is equal to the transpose. So, see, I am a very nice guy. So, it is very easy to find the adjoint. You can just do the transpose, okay. So, basically, the adjoint is the transpose, okay. So, A star equals A transpose for a real matrix. A will be m by n and A transpose will be n by m. When this will be, but see, A is acting on n by 1, u will A is going to be, this is n by 1, this is m by n, and this will be 1 by m, okay. So, basically, see, you do not have a problem if your matrix A square, but V will belong to R n if A is m by n, only then A can operate on it. I get an m dimensional vector. So, this guy has to be an m dimensional vector, m for mother, okay. This is belonging to Rm. So, this belongs to Rm, this belongs to Rn, and here A transpose u, this belongs to Rn, this is Rm, and A transpose is n by m. So, here the inner product will be summed over n terms, here the inner product will be summed over m terms, it is consistent. Okay. Check it, I mean you have to sit down and just take an example and work it out, you will find that it is possible to do the inner product. So, since you asked the question, the A is acting on Rn, A transpose is acting on Rm, okay. U is, the way I wrote it, U is has m dimensions, V is n dimensions. But when I do the transpose, I get n dimension here, n dimension here. When I do the transpose, I get m dimension here, m dimension here. It is consistent. Now, something called a self-adjoint matrix. What is the meaning of self-adjoint matrix? It means the operator is the same as the adjoint. It is adjoint to itself, the operator and the adjoint are the same, okay. This means or A star which is equal to A transpose is equal to A, which means it is A is equal to A transpose, or it is a real symmetric matrix. So, an example of a real symmetric matrix is a self-adjoint matrix, a self-adjoint operator, okay. Is this clear what I told you? Yes, no? I mean, let me just, so see, A is going to act on a vector which has n dimensions because it is m by n, but A transpose acts on a vector which is n dimensions. Eventually, you will get a scalar, okay. Yeah. So, A is going to map Rn to Rm, and this will map Rm to Rn, A transpose, okay. So, finding the adjoint for matrices is straightforward, just take the transpose. And supposing you have a complex, you are working in space where, like I told you earlier, you may have to deal with complex numbers, okay. Then because although your physical system is real, so when you are we are going to be using eigenvalues tomorrow, those eigenvalues can be complex, okay, because they comes in the form of roots of a polynomial equation. Corresponding eigenvectors will be also complex. So, you need to be able to generalize it to the situation where the vectors can actually be complex, have complex elements. So, what if the elements or the vectors can be in a complex space? I mean, complex means some imaginary part is there. Complex does not mean complicated, it means imaginary, okay, square root of -1. Then you have to remember that inner product of u with v is going to be defined as vi. That is what we spoke about earlier when we spoke about the inner products, okay. We said, look, because if you do not put the complex conjugate, then you had this problem of the inner product of a vector with itself becoming negative. So, we had to generalize it and make it positive. Okay. So, this is basically guaranteeing you that inner product of u with u is positive. Okay. So, the length is positive. So, this is the generalization. Now, you can work on the same thing the same way using this, the same approach. We will get A star will be equal to A transpose complex conjugate. Okay. So, basically you can do it, I mean just 2 steps. I mean I only wrote 2 steps, it is actually only 2 steps, although I may have written 5 steps for explaining. Okay. So, basically this is called Hermitian, this is called H, this Hermitian. Okay. So, if A has complex elements, the m and n, the elements of A have some imaginary numbers, imaginary parts, then if you want to calculate the adjoint, you have to take the transpose and you have to complex conjugate it. Okay. You can't just do the transpose. If it is real, of course, complex conjugate does not make sense, you will get the same thing. So, this is the generalization which I want you to keep in mind. Okay. If this complex, you have to transpose and do the complex conjugate, because here you have the complex conjugate in the definition of the inner product. Okay. Most of the time we will be dealing with only square matrices where m by and n are equal, okay, because the number of equations will be equal to the number of unknowns. Okay. If you have m and n, there is a disparity between the number of equations and unknowns. So, most of the time A will be square, and just to give you a preview or a teaser of what we are going to see in the next week, we are going to be working with the eigenvalues and the eigenvectors of A. Okay. We are going to look at the properties of the eigenvalues of A and the eigenvectors of A. First, we will do the properties when A is self-adjoint. Specifically speaking, when A is self-adjoint, when A is real symmetric, the eigenvectors of A are going to be orthogonal. Okay. We will prove that. So, if you have a real symmetric matrix, the eigenvectors will be perpendicular, they will form an orthogonal set, and we will seek solutions in terms of that orthogonal set. That is the whole idea, just to give you the connection about what we are going to do. So, tomorrow, so for a particular problem, I have a specific A, I will, if it is real symmetric, I will find the eigenvalues and the eigenvectors. I will work with these eigenvectors as the basis for constructing my solution. So, then my job is, for given any problem, I have to look at the operator, find the eigenvalues and the eigenvector functions, eigenvectors, eigenfunctions, whatever it is, and construct solutions in terms of those eigenfunctions, eigenvectors as the basis set. So, tomorrow give me some other problem, some other matrix A is there, I will use the eigenvalues of this, because the orthogonality property is there, the solution construction becomes easy. Okay. If I use fix 1 0 0 0 0 0 1 0, you will find when you do the problem, again I have to solve a system of linear equations. So, what happens is, if you are going to use the regular basis function, regular basis 1 0 0, you will end up having to solve system of linear equations. So, might as well solve Ax equals b directly using Gauss Seidel or something. Okay. So, only when you do the problem you will understand this. So, we will do it, then we will see. So, our strategy for the next week will be to understand the properties of these eigenvalues, eigenvectors. We will do the case where A is self-adjoint, we will see how to handle the case where A is not self-adjoint, and again some properties are there, we will use all of that. Then we will look at construction of solutions. Okay.